Imagine a time when the grandest journey humanity could conceive was to leap from our world and land upon another. The moon. It wasn't just a destination, it was a declaration, a statement to the cosmos, that a species, born of stardust on a small rocky planet, was ready to begin its voyage into the cosmic ocean. This shimmering silver disk in our night sky, the subject of poetry, the subject of myth, the subject of wonder, was suddenly within reach. Why did we need such a colossal machine? The answer lies in a race not just against a rival nation, but against the fundamental laws of physics. When President John F. Kennedy stood before the world in 1961 and declared that America would land a man on the moon and return him safely to the Earth before the decade was out, he wasn't just making a promise, he was throwing down a gauntlet. He was defining a finish line in a race that, at the time, we were losing. The Soviets were ahead, with the first satellite and the first human in orbit. To get to the moon, you have to solve a massive energy problem. To escape it, an object must reach a speed of about 25,000 miles per hour or 7 miles per second. That's what we call escape velocity. But we weren't just sending a small probe, we had to send a multi-part spacecraft. A command module, a service module, and a lunar lander. All of this hardware, plus the fuel, life support, and the astronauts themselves, had a tremendous mass. Lifting that much weight off the ground and accelerating it to escape velocity required an almost unimaginable amount of thrust. Building the Saturn V was one of the greatest industrial and engineering undertakings in human history. It was a project that spanned the entire nation, involving over 400,000 people and thousands of companies. The chief architect was Wernher von Braun, a German-born rocket scientist who dreamed of space since boyhood. His team at Marshall Space Flight Center in Huntsville, Alabama designed and built this stairway to the stars. They were the masterminds behind the rocket's power. The SIC first stage required 5 F1 engines, the most powerful single-chamber liquid engines ever built. Early tests suffered combustion instability, engines tearing themselves apart. Engineers built massive test stands in Alabama to tame them. The rocket's size created logistical nightmares. Stages couldn't go by road or rail. First stage, New Orleans. Second stage, California. Third stage, near Sacramento. NASA built a navy of custom barges and even used the pregnant Guppy airplane. All parts converged at Kennedy Space Center. Inside the VAB stages were stacked with watchmaker precision. Every weld was X-rayed, every circuit was tested, every valve was checked, rechecked. They knew astronauts' lives depended on their diligence. They weren't just building a machine, they were building a lifeline. It was pushing knowledge, overcoming failures, and uniting a nation's resources to send a flawless machine to another world. So, how did this magnificent beast actually work? Think of the Saturn V not as a single rocket, but as 3 rockets stacked on top of each other. This is the principle of staging, the secret to escaping Earth's gravity. You shed weight as you go. The first stage, the SIC, was the muscle. Its 5 F1 engines burned RP-1, a refined kerosene, and liquid oxygen cryogenically cooled, a tower of both fire and ice. For about 2.5 minutes they produced 7.6 million pounds of thrust, lifting the vehicle to about 42 miles altitude and over 6,000 miles per hour. Then the first stage was jettisoned, falling into the Atlantic. The rocket was much lighter. Then the second stage, the S-2, ignited, powered by 5 J-2 engines burning liquid hydrogen and liquid oxygen, pushing toward near-orbital velocity for about 6 minutes. After separation, the third stage, the S-4B, took over. It fired to place Apollo into a stable Earth parking orbit. Once all systems were go, the S-4B reignited for the translunar injection, accelerating the spacecraft to 25,000 miles per hour. The Saturn V was a carefully choreographed dance with physics, a disposable masterpiece built to work for about 12 minutes and throw human beings toward another world. In those 12 minutes it threw human beings toward another world. Of all the missions powered by the Saturn V, none shines brighter in our collective memory than Apollo 11. This was it, the moment the entire program had been building towards. On the morning of July 16, 1969, 3 astronauts, Neil Armstrong Buzz, Aldrin Michael Collins sat atop the fully fueled Saturn V rocket, known as AS-506. Below them the rocket held over 1 million gallons of supercooled propellants, a controlled explosion just waiting to happen. On the ground, 1 million spectators gathered along the Florida coast, and hundreds of millions more around the world watched on television. The countdown reached 0, and the world held its breath as the giant awakened. The launch was a sensory overload. The ground shook for miles. The sound was not just heard, it was felt. A deep, crackling roar that vibrated in your very bones. In just under 12 minutes, it had delivered them to their parking orbit around Earth.
That's one small step for a man, one giant leap for mankind.
To truly appreciate the Saturn V, you have to look at the numbers. Standing on the launch pad, the rocket measured 363 feet tall. That's taller than the Statue of Liberty, taller than a 36-story building. If you laid it on its side on a football field, it would stretch across the entire field and pass the other end zone. Its total weight, fully fueled, was over 6.2 million pounds. The first stage engines produced 7.6 million pounds of thrust, equivalent to about 160 million horsepower. More power than 85 Hoover dams combined. The sound at liftoff measured 204 decibels and created seismic shockwaves detected miles away. In the first second after ignition, the 5 F1 engines consumed about 15 tons of propellant, a thirsty giant guzzling fuel to defy gravity. It could launch about 260,000 pounds into low Earth orbit, or about 130 tons. To go to the moon, it could send about 100,000 pounds, 50 tons. The guidance system, a gyroscopically stabilized platform, kept a needle-thin trajectory through the atmosphere and into space. Every part, from colossal engines to tiny transistors, was engineered to the extreme, pushing the limits of technology of its time. A machine that commanded respect, a testament to harnessing elemental forces. The Saturn V's last flight was in 1973, when it launched the Skylab space station. After that, the remaining rockets were relegated to museums. Silent, horizontal giants, magnificent monuments to a bygone era. But the legacy of the Saturn V is not confined to museums. Its echoes reverberate through every rocket launch we see today. The program solved fundamental problems in engine design, cryogenic fuel handling, guidance systems, and large-scale project management. Engineers who cut their teeth on Apollo went on to design the space shuttle. The shuttle's engines and systems drew heavily on Saturn V experience. Today, the Space Launch System is often called the Saturn V's grandchild. Massive, multi-stage, and using the same principles, liquid hydrogen and oxygen, evolved engines. In many ways, we are picking up where we left off, standing on the shoulders of this giant to reach even further. The Saturn V represents more than a technological achievement. It is a symbol of what humanity can accomplish when united by a bold vision and an unyielding will to explore. Its thunderous roar is a perpetual call to the future, urging us to look up, to aim high, and to continue our journey into the stars.